Hey guys, so today we're going to talk about the difference between Euclidean geometry and spherical geometry. Now, first of all, let's kind of talk about geometry in general. Geometry is formed by two words. You've got geo and you've got metry. So geo is kind of about measurements of the earth. So geo means earth. And metry is a form of measurement. Okay, so basically geometry is all about measuring different aspects or measuring different things within the earth. Now there's two types of geometry that we're going to talk about today. We've got Euclidean geometry, which is basically the geometry of flat surfaces. And then we've got spherical geometry, which is the measurements of spheres. Now, we usually use spherical geometry when we're talking about the Earth. So if you look at longitude and latitude, and you look at the equator, we use spherical geometry in order to find that. Spherical geometry is also really important for navigation. So if you're on a ship, if you're like a captain on a ship, or if you're a pilot, you use spherical geometry a lot of the time. Okay, so just a few differences between Euclidean and spherical geometry. So with Euclidean geometry, you have lines, you have line segments, right? In spherical geometry, you have arcs, and you have arc lengths and great circles, right? So if you were to compare these two particular examples, for this first one, it says plane P contains line L and point A not on line L, right? Now, if we were looking at the same kind of similar points, but in spherical geometry, you would say that sphere S would contain the great circle M and point A not on M. Okay, so the great circle M would be a line. Okay, so in Euclidean geometry, again, you're using lines, line segments. With spherical geometry, you're using arc lengths and great circles. So let's look at this next example. So it says the vertices of triangle ABC are points in plane P, and the sides are segments. The sum of their interior angles of a triangle is 180 degrees, meaning measure of angle A plus measure of angle B plus measure of angle C is all going to equal exactly 180 degrees. Okay? Now, in spherical geometry, we would say that the vertices of triangle ABC are points on sphere S, and the sides are arcs of great circles. The sum of their interior angles has to be greater than 180 degrees. This diagram down here is wrong. This should actually say must be greater than 180 degrees. Okay? Now, the smaller the triangle is, the spherical triangle is, the closer it is to 180 degrees, but it's never exactly 180 degrees. And the greater it is, the larger the great circle. The larger the spherical triangle. So let's kind of look at some examples, some differences between Euclidean and spherical geometry. I actually want you guys to go ahead and pause this video and try to solve this on your own. Try to find the parallels between the Euclidean statement and the spherical statement. So go ahead and pause the video now. Alright, you guys should have attempted this portion. So for this, we're trying to find the parallel statement of a line has a segment. So if in Euclidean geometry a line has a segment is true, in spherical geometry it would be that a sphere has an arc. Okay? So segments in Euclidean geometry are arcs in spherical geometry. One line between 2 points. Okay, Now, that's true in Euclidean geometry, but in spherical geometry, let's kind of think about this. If we have a circle, and we have 2 points within that circle, you can actually have several great circles going through those same 2 points. So actually, that's not the same thing when we're talking about spherical geometry. So there's actually infinite lines between 2 points when we're talking about spherical geometry. Now, in Euclidean geometry, it says that a line can extend infinitely. Now, if we're looking at lines within a sphere, if we have lines within a sphere, that sphere is just going to be the length of a great circle. It's not going to extend any further than that. It's going to stop at the great circle, right? Okay, a line can intersect at 1 point. All right. So in Euclidean geometry, if you have 2 great circles, they're actually going to extend at exactly 2 points, right? You've got one up here and also one down here. So they actually extend at 2 points and exactly 2 points. Okay, so I actually do have more examples. I actually posted a video titled Euclidean versus Spherical Geometry. Please make sure that you watch that. It's got a lot of information on it. Really good for you guys to know. So make sure that you watch that video. All right, moving on. So earlier I kind of briefly mentioned spherical triangles. So these are triangles formed whenever you have 3 or more great circles. So it'll create a kind of a triangle with curved edges. And those edges are basically arcs, right? So in order to do this, in order to find the area of a spherical triangle, you would do area equals pi r squared over 180 times the measure of angle A plus the measure of angle B plus the measure of angle C minus 180 degrees, where r obviously is the radius of the sphere. Okay, so it's very simple. You're just going to plug in the values into that formula, and you should be good. Now you will be provided with this formula, so you don't have to actually memorize it. All right, so let's look at example 1. For example 1, it says use the diagram and the given arc measure to find the distances between point A and point B. Okay, so we kind of talked a little bit about this earlier, I believe in Unit 11, actually, in Chapter 11, if you can remember that far back. But basically what we're trying to find is the arc length of AB. And actually, because it doesn't specify, because it just says the distances between A and B, you actually have to write both distances. So you have arc length AB, but then also you have another possibility here, which is this. So between A and B, you could actually even look at the arc length of ACB. So you could either look at the major arc or the minor arc. We're going to actually find both since they don't specify. All right. So in case you forgot, you are going to have to set up a proportion. You're going to have to always do part over whole. So you'll do the arc length over the total circumference, and then equals the central angle of whatever arc length you're trying to find, over the total, which is 360 degrees, obviously. So let's start off by finding the arc length of AB. So I'm going to just call the arc length of AB, I'm going to call that X, and then I'm going to call arc length of ACB, I'm going to call that one Y, just because it makes things easier so I don't have to write the entire thing all over and over again. So anyways, let's start off by finding arc length of AB. So arc length of AB, x, is going to be over the entire arc length, the entire circumference, which is going to be 2 pi r, right? But since they're giving us the diameter, you could also just use d pi, right? So this would just be 14 pi. And then that equals, now if I know that the measure of arc AB is 100, then I know that its corresponding central angle is also 100. So I'm going to say 100 over the total, which is 360 degrees. Okay, I'm going to go ahead and simplify that. I'm going to multiply both sides by 14 pi. So then I end up with x is equal to 35 over 9 pi, which is approximately 12.2, right? So that's 12.2 feet. All right, so I just found the minor arc. I'm now going to find the major arc, which we said is y. To find y, since I know that my entire circumference is 14 pi, and I know that my minor arc is 35 over 9 pi, I can just subtract the two to find the major arc. So that's what I'm going to do. I'm going to do 14 pi minus 35 over 9 pi. Notice that I used 35 over 9 pi and not 12.2 feet. If I use 12.2 feet, that's intermediate rounding, and that will give me the wrong answer. Please make sure you don't do that on a test. So when you plug this into the calculator, you get approximately, y is approximately 31.8 feet. So these are the two different distances, the two possible distances between A and B. So let's do the same thing with question 2. So for question 2, we're given that the measure of AB is 50 degrees, which means that the corresponding central angle is also going to be 50 degrees. Okay, I'm also given the diameter is 8 millimeters rather. So I'm trying to find the two different distances. So again, I'm going to call arc length AB x, and I'm going to call arc length ACB y. So I'm going to do this again, the same thing. So I know that it's going to be x over my total circumference, which is going to be 8 pi, equals, and then it's going to be 50 over 360 degrees. So once again, I'm just going to multiply both sides by 8 pi. You end up with x equals 10 over 9 pi, which is approximately 3.5, and that is millimeters, 3.5 millimeters. Okay, so now for y, I know that my total circumference is 8 pi, so I'm going to do 8 pi minus 10 over 9 pi. So then I get that y is approximately 21.6 millimeters. Alright, I want you guys to pause this video and try the next two on your own, and then we will go over them. Alright, so looking at question 3, we're given that the measure of arc AB is 25, which means that the corresponding central angle is also 25 degrees. So I'm going to go ahead and set up this proportion. So I'm going to call AB x, I'm going to call ACB y. So I have x over 20 pi is equal to 25 over 360. I'm going to multiply both sides by 20 pi. So I get x equals 25 over 18 pi, which is approximately 4.4 centimeters. Okay, for y, I'm going to do my total circumference, which is 20 pi, and then I'm going to do that minus my my minor arc, so minus 25 over 18 pi. So I get that y is approximately 58.4, and that's 58.4 centimeters. Okay, moving on to question 4. So I'm going to do the same thing. I'm going to call AB x. I'm going to call AC y. So I'm going to do x over my total circumference, which is 40 pi. And that equals my central angle, which is 125 over 360. I'm going to multiply both sides by 40 pi. I end up with x equals 125 over 9 pi, which is approximately 43.6 inches. Okay, for y, I'm going to do my total circumference, which is 40 pi. I'm going to subtract 125 over 9 pi, and I get that y is approximately 82.1 inches. Okay, now guys, I cannot stress enough that you need to make sure everything is an exact form until the very end. Remember, if you do not do that on a test, you will get it wrong because the rounding is going to be off. Okay, so make sure that you round, and especially now that we're not, since we're doing this online learning thing, it's going to be very hard for me to check your work and all of that fun stuff. So please make sure that you keep everything in exact form until the very end. Alright, so let's look at questions 5 through 8. Question 5 through 8 asks us to find the area of the spherical triangles. So we're just simply going to use the formula that they gave us, which is that your area, and put this somewhere over here off to the side. So my area of a spherical triangle is going to be pi r squared over 180 times measure of angle A plus measure of angle B plus measure of angle C minus 180 degrees. Okay, so we're just going to simply use that formula to find each of these spherical circles, or spherical triangles. Okay, so I'm going to go ahead and plug in what I know for this first one. I know that my radius is 3, so I'm going to do area equals pi times 3 squared over 180 degrees times 86 plus 115 plus 114 minus 180. I'm simply going to put that in the calculator exactly as is, and I get that my area is approximately 21.2 feet squared, because this is area, so feet squared. Okay, let's do this next one. So again, we're given that the radius is 9, and then we're given the 3 angles for the spherical triangle. So we're going to do pi, so area equals pi times my radius, which is 9 squared, over 180 times the sum of my three angles. So I've got 50 plus 90 plus 85, and then I'm going to subtract that. I'm going to subtract 180 from all of that, and I'm going to put that in the calculator exactly as is. I get that my area of the spherical triangle is approximately 63.6 yards squared. Okay, go ahead and pause this video and try the next 2. Alright, you guys should have tried these next 2, so let's go ahead and do this. So for question 7, we're given the diameter. Obviously, we need the radius. The radius is just half of that, which is just 12. So again, I have my area equals pi times 12 squared over 180, and then times the sum of my 3 angles minus 180. So I'm going to do 111 plus 111 plus 138 minus 180. And then whenever I plug that into the calculator, I get that my area is approximately 452.4, and that is centimeters squared. Alright, looking at question 8, again, we're given the diameter, so the radius here would be 7.5. So again, I'm going to do this. I'm going to have pi times 7.5 squared over 180, and multiply that by the sum of the three angles. So 48 plus 94 plus 128, and then I'm going to subtract 180. And I'm going to plug that into the calculator exactly the way that it looks. So then I get that my area is approximately 88.4 inches squared.